All right, so that leads us back into these 3 true falses, which is about fitting in data. And all of these are phrased as it is always better to blank, right? It's always better one thing or another thing. This matters a lot because in real life you will have choices, right? You won't just have one model. It won't just be run the model and fit it. You can do anything you want, right? And when you're doing anything you want, it's important to think of what is better to do. So, you might say, okay, like somebody just told me how many variables to use and I ran it, right? But in real life, you get to pick how many variables, and that's why it's good to know what is better. Is using more variables better? Is using a higher power better? Is having an R² value that's high, is that better? Okay, maybe I'll do 30 more seconds for the people who just walked in to put in guesses. Any other questions or comments while we're waiting for people to put in their final answers for the first question? Okay. So I'm hoping to have a little bit of time towards the end of the class today. We'll just talk about practical things for the project and maybe give you a boost, and you can try to work hard this weekend and get most of that done. Okay. Let's take a look. On the true falses, what do people think? So let's reveal the counts. All right, true or false, in a large data set where X is multidimensional, it is always better to use more variables in the model. We have 14 false to 3 true. So most people think it is false. The correct answer is false. I won't hit reveal because then it would reveal all the answers. But the correct answer is false. More variables is not always better. That is what the videos for today's class were all about. You don't want to use too many variables sometimes because it can lead to overfitting, and you want to be careful for that. Was there a question? Anybody? Okay, so that's what the videos are about. We're going to run some examples of this. Okay, what about polynomial regression? So if you have something that's one-dimensional, you can do polynomial regression. So instead of doing beta 1 hat times x, you can do beta 1 hat times x plus beta 2 hat times x squared, and so on. And that's called polynomial regression. And the question is, when running polynomial regression, is it always better to use a higher power, the higher powers, the more powers you use? And people said false. People said false. And false is, again, the correct answer. So very well done, everyone. This is actually the same thing as before. You can think of the powers as higher dimensional things, right? So instead of having just x, you have x and x squared. Yes, they're related in some way, but it's just another dimension. So really, this one and this one are the same question twice, right? Which is, should you have more or less variables? And you guys all watch the videos, you know that you don't always want more. Okay. Last one, true or false? When running a regression, it's always better to have an R² value. If you run it twice, you always want to pick the one with the higher R² value. And this one, 13 to 4. So not quite as clear-cut as the other ones, but also false. All 3 of them were false. So you don't always want a higher R² value. And in fact, the more variables you use, the higher the R² value you get. So in the first 2, using more variables or using higher powers will always lead to a better R² value, but you don't always want a better R² value because the R² value measures how you're doing on the training set. And sometimes if your training error is very, very low, that is not the best thing, right? You want your test set error to be low, not your training set error. So it looks like you guys all figured this out. I couldn't trick you guys. False, false, false. Everybody got it, or most people got it. Any questions or comments about this idea? Okay, and that's what you're going to have to, in your project, when I say show me overfitting and show me underfitting, one of the things you have to show me is the test error is very different than the training error when you're overfitting. So you'll have a very good R² value or a very good training error, but your test error will be quite bad, and that's one way to demonstrate what's going on. Okay, so this is important. You can't just go by the R² value. You have to do something else. And in the videos, they mentioned these 2 options. So instead of using just the R² value or just the training error, that is not good. Don't just do that. You have some choices. You can use a test set, like we talked about, or they mentioned these adjusted R² scores. These are things like AIC, something information criteria, BIC is, I think, the Bayesian information criteria, CP, etc. So these are measures that are more complicated than the R squared, that kind of adjust the R squared. Some of them have a formula that says the R squared minus something. So these are the adjusted R squared scores. And I will let you pick which one you like better. Do you like the test set better, or do you like these cool adjusted ones better? They have some pros and cons. So one of them is not always better than the other one. There is no mathematically correct answer. But I'll let you think for 1 minute and tell me what you think. Okay, let's take a look. What do people like better between these two? 19 people said use a test set. 6 people like the adjusted scores. And again, there is no right or wrong answer. They have pros and cons. Does anyone want to tell me a pro of these adjusted scores compared to the test set? So in what way is that the adjusted one's better than the test set?
They can use it during the development phase. So which cannot be done at the test set, which will be done at the last to test how good our model is.
Okay. Yes. Okay, so good. This is you're saying, yeah, you can do it like while you're doing stuff. Yes, okay. I like that. Yeah, there's another way to phrase the same idea, which is what I was thinking of. Very related. Yeah, so sometimes people they say we have the training set, and then the test set is like the thing on the leaderboard, right, that you don't have the answers to. Like this thing is the test set. And there is a third type of set that is somewhere between the training set and the test set, which is called the validation set. Who's heard of a validation set before? So validation set is also a type of test set, but the only difference is the validation set you think of as being part of your training set, right? So you took your training set and you split off a little piece of the validation set. Some people will just call that a test set. You know, I had my data, which was 1,000. I took 200 of them. I made that my test set. So whatever you want to call it, either test or validation, that can be part of your training set. So for example, I gave you guys, in project 1, I gave you guys 1,000 houses, and I asked you, please show me underfitting and overfitting. And when you show me underfitting and overfitting, you can't use the test set because you don't know the answers. You're going to have to make your own test set or your own validation set by splitting off part of it, or by using some of these things. So this is a good distinction. So with that distinction in mind, what's another way to phrase the advantage of the adjusted R squared scores? Yeah.
For an extremely complex model which might take even days to train, I think that test set to justify which variables we should pick should not be a correct way, because then once you have developed a model, it took you, let's say, 1 month to train it. And then, so that way it will become complex. And second, I think that
Wait, sorry. What does the first thing have to do with the adjusted R squared score? Are you saying, suppose the model is very complicated. Okay, I agree. There are models that are complicated. That means the adjusted R squared score is better because?
More number of variables.
But wouldn't the test set also have, like, the test set would do the same thing? So we're trying to say, why is the adjusted R squared score better than the test set?
So we can do it before training.
You do it before training.
So basically it is AIC, DIC we use to reduce the dimensions of the data.
Okay, so you're saying, look, we have a big complicated model we're going to run at the end, and we're going to decide which one to do first. And we can use the AIC, BIC, et cetera, to choose which one we're going to do first, and then we run the big one that takes like a month to train.
Yeah.
Couldn't we also use a test set to do the same thing on the first page? We choose what we want to do with the test set, then we run the big complicated model, it takes a month. So in that sense, I think they're equal. They both can tell you what is better and worse before you commit a lot of resources to something.
Yeah, and the second thing I was going to say, like Puller taught us a lot of things related to medical field. So, sometimes we don't have knowledge about data so well in the field. So, at that time, we might not be able to correctly justify using a test set. So,
Okay. So you're saying if it's, I think. Let me paraphrase what you're saying. You tell me if I got it.
We can actually justify correctly using AIC, BIC.
Okay. So you're saying if it's very complicated, we don't know what's going on. There's like we got some crazy numbers and data that's like hard to understand. Then you're saying the AIC BIC is better than the test set. Why is the AIC BIC better than the test set if we don't know what's going on?
Because they give us a statistical way of verifying that it is correct or not.
I see. So you're saying you can always apply it no matter what. It's like no matter what the data is, you can always apply the AIC BIC things on it. Can you not apply the test set thing no matter what? Is there a reason you can't apply the test set?
We can apply.
I think you can, yeah. I think all the things you're saying are advantages of both, right? There's and this is like why data science is hard, is because you can't just run the big model, right? You got to think a little bit first, like which big model are we going to run? And both of these are ways to figure out if you're overfitting, choose the best model, stuff like that. But they both do both. So I don't think the things you're bringing up are just advantages of both of them. Not necessarily only for one over the other. Okay. Anyone have any other ideas?
If there is less data, then it's very hard to separate a test set.
Yes. Okay. This is great. So this is a great comment. If you have a small amount of data, and then you want to use a test set, what do you have to do? Is you have to cut some of the data out of your training set and say, this stuff we're not going to use in our training. We're going to put it aside to be the test set. Or the validation set, if you want. So anytime you use a test set, you have to peel off a little bit of your data to be in the validation or test set. And if you have a small amount of data, this is a big problem. If you have a big amount of data, it's still an issue. Like you're making the model less good than it could be, right? You had 10,000 pieces of data and you said, I'm only using 8,000. So anytime you use a test set, you have this disadvantage that you're reducing the size. Okay? And that can be a big problem if it's a small set. If it's a big set, maybe it's just a percentage like not goodness and it's not a big problem, but it's always something you got to deal with. So using a test set always has that disadvantage. And when you use these scores, you can do it on the entire thing. So very good. Okay, so that we just said one pro or one con of these. Let's write that down so we can remember it for next time. So let's say test set versus adjusted R squared, and they both do the same thing. They both help you evaluate your models. But a test set, a con, let's write it this way. Con for test set must reduce training data size. Reduce training data size. So when you peel some data off of your training set, you're reducing the size of your training set. Okay, very good. Can we think of a con for the adjusted R squared? What is the con for the adjusted R squared? Why did you guys everybody said they liked using a test set. Why don't they like using the adjusted R squareds? Yeah.
Maybe the case that the R square value is high, but the test results are showing negative.
Right.
The results are false.
Okay, this is fantastic. So this is exactly what we did in the first exercise, right? We were talking about you don't always want a high R squared value, you don't always want a lot of variables. And you're saying, if there's a situation where the R squared value is very high and the test set value is low, the test set tells you right away. Wouldn't the adjusted R squared also tell us though? Like, isn't that the point of the adjusted R squared? It's like you take the regular R squared and you kind of adjust it a bit, and it's supposed to tell you what would happen on the test set. So I think you're right, but do you mean the ordinary R squared or do you mean the adjusted R squared?
I mean the ordinary, but
Okay.
also it may be the case for adjusted R squared.
Uh-huh.
I'm not sure with the example, but it may be the case.
Okay, yeah, so maybe you're thinking, is there a situation where the adjusted R squared would not pick up the fact that actually the test set error is very bad. Right. Okay. And then I think this is maybe the reason everybody chose this one. This one, the adjusted R squared scores, they require some kind of faith in the like Bayesian stats modeling papers from like the 1970s where they invented this stuff and they said, look, if you take the R squared score and you adjust it by this much, that will be a proxy for the test score. But it's all you're never sure, like, did it really work? Whereas if you use the test set, it's kind of very clear what's going on. So maybe the way to say what this is, the con is it's harder to be sure it works. Harder to be sure it's working. Right? So you run it and you're not, maybe you run it and you're like, okay, the adjusted R squared is so much, but is it really working well on the test set? We don't know. And again, for a lot of things, you don't actually need to know you don't need to know the absolute value of the test score. You just need to know between two models, which one is going to have a better test score. So sometimes the adjusted R squared, even if it's not accurately telling you the test score, as long as like the sort of relative amount for the two models you're testing is right, then maybe the adjusted R squared could still be useful. So even if it's not telling you the actual number, it could still be useful as long as it tells you which one is the best. But in any case, it's always harder to be sure that it's working. If someone says like, how good is the test set going to be? Like when I deploy this, when we spend millions of dollars in Netflix to deploy this on our servers, how many more views are we going to get? You're like, well, I don't know. The adjusted R squared, we subtracted off this amount, and we picked the best model, but we're not sure. So I think that's one issue. Anyone else have any other issues? Why did 19 out of 21 people pick this one? Only 6 out of 21 people picked this one. So it seems like you guys really do like the test set better. I guess another way is, what is another pro of the test set that you like?
Adding on to what you said, actually, I have experienced this thing, harder to detect. So once even I got that adjusted R square was quite faulty and leading me wrong way. So like in my bachelor's, I trained a model on same house price, and in it I got that after removing the crime rate variable from it, the adjusted R square was getting better due to some BIC factor. And test set was going wrongly. I mean, test set was negative. So, like thinking with common sense, criminal rates should not be taken out when you are considering house prices. But I don't know why it was showing. Maybe data was
not only is it hard to be sure it's working, it sometimes doesn't work. Sometimes doesn't work. And why does it sometimes not work? Well, when the people who invented adjusted R squared invented it, they said under these specific circumstances it works. And so if some of the assumptions are violated, right? They proved a theorem that said under this and that specific circumstance, this adjusted R squared is going to work in the following way. Are you in this and that specific circumstance? Well, for one thing, you have to understand what it is. You have to go read the paper. So sometimes it doesn't work, and because assumptions need to check assumptions, which can be tricky. And even if you understand the assumptions, maybe they are hard to verify, right? So like maybe there's an assumption that such and such data column is distributed like a Gaussian or a normal random variable. And you're like, okay, I have 100 samples of it. Here are my 100 samples. Is it distributed like a Gaussian? I don't know. Like it would be hard. You have to do some work to check and see if these things are working. So adjusted R squared, I think of it as like a more niche thing. Like in some particular circumstances, it's great. You don't have to reduce the training set size. It's like you have a special screw, right? It's like just the right size. You get the special screwdriver and you can do it. Whereas the test set is just like you get a drill and you just like through. And it doesn't matter what it is. You can always do it. You're going to break some stuff. You're going to reduce the training set size, but it will always work. So the big pro of the test set is that it is more general. And I'll give you one specific example is these adjusted R squared things. If you start doing like neural networks or these like modern things that have billions and billions of parameters, these adjusted R squared scores don't work at all. So for example, they say like every parameter you add you should be subtracting from the R squared. But neural networks are sort of built in this very different regime where things are extremely over-parameterized. You have like a billion parameters, and each parameter sort of doesn't matter very much. And in those regimes, this adjusted R squared is just not right. You would get like a negative R squared value if you're doing these things. So the adjusted R squared, when it works, it's great. It's hard to check when does it work, when does it not work. The test set always works, but you have to reduce your size. And for that reason, I think this is the last time we'll mention the adjusted R-squared. So for the rest of the course, we're going to focus on always using a test set. This will be our choice for the course. Of course, the adjusted R-squareds, you can study them and get your PhD in adjusted R-squareds if you want. But we're going to stick with this one because it's very general, it's easy to apply. The big downside is you reduce your set by a bit, and we'll talk about different ways to mitigate that. So we talked a little about leave one out or cross-validation, which try to help you recover bigger training set sizes. So we'll talk about that as we go. But we're always going to do stuff with test set. Okay. Any other questions or comments about that? It seems like you guys are on board with that since almost everybody chose the test set. Okay, so in the rest of the class, I have 3 little notebooks that are very practical to go through these using a test set in a really specific situation to try to find the best model and just practicing that skill because that's what you'll be doing on the assignment. So I have 3 kind of like baby ones that are all pretty quick. We'll do those, and then I have some time at the end where you guys can ask questions about the actual project. We can look at the actual data you have and start thinking about some practical questions like, what are you going to do? What's your first step going to be for the project? Okay, so to start with, I'm going to do, let's do this polynomial one, which was mentioned. So let's see, can I click on this? So this is, again, all on the course GitHub. And it's choosing the best polynomial to do a polynomial regression by doing test set stuff. So I'm not going to do any of this R-squared, adjusted R-squared things, only the test set. And the data set we're using is the auto data set. And we have this data. This is the data. We're doing it. I have the horsepower of a car, and then I have the miles per gallon. So the more horsepower you have, it's a very beefy car. It can go really fast. Sometimes the less miles per gallon you have. And so there's some pattern like this where it looks like this. And our job is to make a model that predicts what is the miles per gallon as a function of horsepower. So that's the data, the autos data set. And you can see, again, I won't go through it in a super lot of detail over here. And of course, there are many, many good resources online. But if you want some examples of how to use these pandas data frames and stuff, and sklearn to make polynomial features, this is a good place to go. So you can copy paste this into your code if you want for the project, where we've made this auto data frame, and it has things like horsepower, horsepower squared, horsepower cubed, and so on. And here it's doing this polynomial fit and stuff like that. Okay, so there's the data. And here is what I did is I split it into a test set and a training set using this sklearn train test split function. And so that will automatically take out a random 20%. Here is what it looks like. Here's what it looks like. I take XY and I say test set. I made it 50%. So I made a really beefy, big test set. If you make your test set too big, then the problem is that your training set is small, right? So you're going to have a very accurate idea of how well you're doing, but you're going to be doing something that's quite a bit underpowered. So it is up to you what you want to do. For the purposes of demonstrating how this test set stuff works, I made it really big so that it doesn't change too much. We'll see another example where it can be a little bit different. What am I thinking of? Okay, well, we'll see. Okay, so here we go. So I took this linear regression thing. Again, I'm using sklearn. You can read about the syntax, or you can copy paste the syntax as a starting point online. And I fit it, and then I have these plots that were generated. And let's see if we can put them on screen a little bit more. Okay, so this is the linear model. So just using a linear function, y equals mx plus b. The green points are the training set, and the red points are the test set. And so every blue point is some real point, and it gets mapped down to somewhere on this line. So like, for example, these two at the end, they were both green points, and we're quite a bit off on those ones. So we got a big thing over here. On the red one, we have a little bit less. And you can see that the test mean squared error is 25.5, and the training mean squared error is like 23. It would have been better for me to do the root mean squared error, because now I have to do square roots in my head. So 25.5 the square root is like 5. So it's saying we're off by about 5 units on average. So that's about this much. That kind of adds up. That's like roughly how much we're off. But you can see the test error is a little bit higher than the training error. If we were doing an adjusted thing, the adjustment would be, okay, take 23.16 and add like 2 to it, right? And that would tell us the test set error is a little bit higher than the training set error. But we're not doing that because it's hard to get right, so we're just going to do training test set. Okay, that is a linear one. The next one is a quadratic one. So in this one, we used 2 variables. So we did y equals, we went from doing y equals beta hat 0 plus beta hat 1x, that's what we did before, and now we're doing this, y equals beta hat 0 plus beta hat 1x plus beta hat 2x squared. And once again, same warning as last class. Even though these 2 things are called beta hat 1, you should think of them as completely different things that have nothing to do with each other, right? So this model and that model are completely different models. This beta hat 1 and that beta hat 1 will now be completely different. Okay, and if you look at it, you'll see what happened is that the training error went down by quite a bit. The training mean squared error went down to 16. Big improvement in the training error. But the test error, 22.22. It went down a little, not very much. And you can see roughly how it's doing. It's nice to visualize this because it's one-dimensional. In your actual problem, you have 80 columns. It's going to be quite tricky to visualize things. You're going to have to come up with good ways to visualize and convince yourself that it's doing what you think it's doing and debugging it and so on. Okay, but that's what it looks like with 2. And then with 3, it looks like this, kind of similar. And by using a higher power, we can kind of do some weird nonlinear stuff where it kind of flattens out here, like we think it should do. And you can see the training error went down again. So before it was, what was it, 16.8, and now it's 16.6, which is quite a big improvement from the 23 that it was over there, but it's kind of not improving as quickly as it was before. Okay, that's 2, that's 3. Okay, here's another one with 4. So 4 powers. And you see the test set is kind of barely moving. It's always around 22. So even though we're using a more complicated model, the actual score is not improving. And the nice thing to do is to plot what it's doing. Here's power 5. And you can see here it's doing some wonky stuff over here. It goes up right at the end, right, to do these things. Okay, and here it is plotted of trying it a bunch of times. So here I did it with a 20% size test set. And this is what it looks like. So as a function of the polynomial power. So this is either 1, 2, 3, 4, or 5, either a linear function, a quadratic function, a cubic function, a quartic, or a quintic. And you can see the training error is always going down. The more powers you use, the training error is always going down. And this is the true false that most people got right, is even though the test error is always going down, or sorry, the training error is always going down, that doesn't mean you necessarily want to use the highest power, because the test set goes down and then goes back up. So you want to find where the test set error is minimized, which looks like 2 or 3. And then it's going up just a little bit over here. Here is one thing you should be aware of, is that all this stuff is random, right? We did the test set, which was 20% of the data, chosen at random. If you choose a different 20%, you're going to get a different result. So if we rerun it again, we should get something new. And so the size of the test set you use will change things. Oh, it's going to yell at me. Let me run everything. Okay, hopefully this works. Okay, and so it is worth your time for these small models where training them doesn't take months and months to rerun it a bunch of times to try to understand what is it doing sort of typically on average. So here it is again, and now let me rerun it. It should give us a different one. Okay, unless it doesn't, I don't know. We're gonna find out. Okay, just gonna click it. I'll just say it's already running. Okay, great. What don't you like? Okay, it finished. So we ran it again. Look, this looks very different, right? So in this one, it looks very different. Before, they were the other way around. This one makes more sense. The test set error is a little bit higher than the train set error, but they still have the same shape, right? The training set is going all the way down, the test set goes down, and it kind of goes back up. And you could even say, like, let's run it a bunch of times and plot them a bunch of times. So I put this number of retries. Let's do it 10 times. Let's do 5 times to be certain. Let's do 4 times so we don't get confused with the number 5. So here I ran it 4 different times. And you can see the test error is jumping all over, right? It's going up and down and up and down. But the thing that is nice is the minimum of the test error is pretty constant. It looks like the minimum is always either 2 or 3, right? It always has kind of, it goes down for 2, kind of flattish towards 3, and then it goes back up again. And the training error is always doing this thing where it's always going down. This always going down shape, as you make the model more flexible by including more powers, you'll always see that, right? The training error will always go down, 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 down. So this kind of blue curve is kind of like not that helpful, except for seeing that it's working. Okay, so based on this, if this was my project, I would probably pick power 2 or power 3 and run that. If everything else is equal, it's kind of better to pick the simpler model. So I would probably pick 2, just in case there's some weird stuff. Another option you can do is you can do this leave one out cross-validation. So this is how to do it with sklearn. In leave one out cross-validation, you're going to rerun the model many, many times using 1 point as the test set each time. So here I ran it 5 times, but you could run it, hundreds of times with a test set of size 1. And here is the number of times we're going to run the model, 392 times. And here is what that looks like if you do that. Here's the leave one out error. And you can see it does the same kind of thing. It goes down, and it goes up a bit. And then funnily enough, at 5, the leave one out error is even lower. So should you do 5 or should you do 2 here? This is like a choice you're going to have to make. I would do more testing to investigate this because, this to me, I'm nervous. Like, why is it lower here? Whereas in the other ones, it was not. So it could be something about the leave one out error that could be, not working well. So you'd have to make a choice. You could investigate more. But this is how I would pick the polynomial power. And the last step, not listed here. Oh, there's another option, which is k-fold cross-validation. Again, there's a package for that. So before I was running size 20% chosen independently. This runs 5 that are 20% that have no overlap. And same kind of deal. You get something like looks like this. Okay, and in the k-fold cross-validation again, it seems to go down a little bit at 5. So maybe you do want to include 5. I don't know. You'd have to decide. If this was the actual project, you could submit both models, the 2 model and the 5 model. You could submit them both to the leaderboard and see which one does better on the real test set. Right? So far we've only used our made-up test set from the training set, but you could check with the actual thing, which one's better if you have 2 that are close. Okay. Any questions or comments about this CARS model, choosing the best polynomial power? Okay, and again, the code is on GitHub, so this probably will be helpful for you guys to see the code, and you can copy paste various ideas out of it as you use them. All right. Okay, in the next one, it's even more similar to the project you're doing, and this is the subset selection problem. Let me run all. Runtime, run all. And it follows. This is actually following the lab from the actual textbook. So if you go to the textbook and you look at the lab they have in the textbook, it's exactly this thing. They have example code, and this is very similar to their example code. So you can follow either way. Okay, and this is using a different, instead of sklearn, it's using the stats model API. So you can use either one. And what this one is the hitters database. So these are baseball players. Here's a whole bunch of baseball players. And here's a whole bunch of baseball stats. How many times were they at bat? How many hits did they get? How many home runs did they get? I don't know. These are numbers that have something to do with baseball. I don't really know it. Okay. Some of these are 0-1 value, which is just like your data set, right? Which division are they in, and so on. And did I have to actually do that? Yeah, okay. This is something we'll talk about in a bit. I created these things, league and division, in the original data set. They were not numbers, they were letters. It was like, which league are you in? Oh, I'm in the North American League. So it would say, under league, it would say North America or something. And then I use this function, pandas.getDummies, and that will convert from letters into 0s and 1s. And so I've made sure that everything in the table is 0s and 1s, because then when I run linear regression, it's all fine. We'll talk about this more in a few minutes if we have time at the end. Okay, so there is the data set. And the question is, can you predict, that's the X, can you predict how much they are paid? So the Y is how much they are paid. I think the units are hundreds of thousands of dollars. So these people, 475. It's not that he's getting $475. He's getting $475,100,000. So you know, a lot of money. Okay. And the question is, can you predict using this stuff? Try to make the best model to predict their salaries. This is very similar to what you guys are doing. This is like a baby version of your project, because in your project you have 80 columns. This only has 19 columns. And you guys have 1,000 data points. Here there's only 263 data points. So it's like a baby version of that. Okay, and we just implemented this idea of trying lots of models with different numbers of variables to see what is the best one. So same train test split as before. You could do it with the adjusted R squared, but I'm not going to. And then I have this function that I wrote to process the subset. So given some set of features, run the regression with just the features that you told me, and report back the root mean squared error. And I save everything using these dictionaries. So these dictionaries over here report back the results. So the number, the features you had, the number of features you had, the model, which is some Python object that can do predictions and stuff, and the amount, the root mean squared error. And so by doing that, I can keep track of, every time I run one of these, I can write down the result and look at them later. So this is processing one subset. And this forward function is exactly what was described in the video of doing this forward selection process. So you start with no variables and you add on one variable at a time. You try all the things with adding on one variable and you see which one is the best. You add that in and you keep going. So you can see how it's going. It's trying all the things and adding on the best one. So it takes the best one, the best model, and then it returns that. Okay. And this code does the forward selection. And it outputs something that looks like this. Okay, so we start out with a model that has nothing. And what are we going to add in? We can add in the number of at-bats. We could run a model with only the at-bats. We could run a model with only the hits. We could run a model with only the RBIs, and so on. And there's like 20 choices because there's 20 columns. I guess there's 19 columns. And for each one, we calculate the root mean squared error. So this is exactly what they did in that video of the forward selection. This is the first step of forward selection. And we want to pick the one that is minimal. So which one has the best root mean squared error at 410, 393, 400, 373. That's got to be good. Oh, 372. 372. I think that's the winner. Okay, so 372 is the winner. The best thing is option number 10, the C runs. What is the C runs? I don't even know what C runs is. Some kind of run. The cool runs. The more cool runs you have, that seems to predict your salary very well. So if you know how many cool runs somebody has, that is the best. So the computer says, okay, we picked C runs. Let's look at all the models that include C runs and one other variable. So here it is, C runs and at-bats, C runs and hits, C runs and home runs, C runs and RBIs, a whole bunch of things. And I guess there's going to be, before there were 19 options, you can't have C runs twice, so now there's going to be 18 options. So starting at number 0 and going all the way up to 17. Let's see, can I zoom in even more? Okay. And you picked which one's the best. So which one is the best? 333, and you'll see it's going down, right? 320. What's the best one? Is 320 the best? 320 the best. 305. Wow, that's great. Okay, 305. So if you do C runs and putouts, what the hell is a putout? I don't know. That's golf, isn't it? Putting? Okay, anyway. That's the best one. So then the model's like, okay, we'll do C runs and putouts, and we'll look for one other variable. I think you guys are getting the idea now. And it keeps going and going and going. And it runs it a whole bunch of times. Like they explained in that video, you try approximately p squared over 2 models. So when p here was 18, p squared divided by 2 is a reasonable number. You guys are going to have 81 squared. So you guys have 4 times as many columns. If you were to do this, it would take you 16 times the amount of work, because it goes by the square. Can you run 16 times the amount? This one ran in 0 seconds. So 16 times the amount of work. Maybe it'll take you 16 seconds or something. Should still be doable if you want to do something like this. And here are the models that it computed. So it has the model. All the best models are saved with 1 variable, 2 variables, 3 variables, 4 variables, and so on. All right. And you can see the RMSE is going down, 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 down. And then the RMSE starts to go up, 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 up. So the model with 19 variables is worse than some of the models that had 2 variables, and so on. And you can see that very nicely over here. Here's a nice plot showing the number of predictors versus the root mean squared error. Let's zoom out so we can get the whole plot in there. Number of predictors, and it took the best model from each class during the forward selection. So okay, of course, just saying number of predictors doesn't tell you all the details. You need to explain all the details in some caption or something. With one predictor, quite a lot of root mean squared error. It dramatically went down for 2, and then somehow here when we got to 8, it went down a little bit more, and the minimum was this highlighted one at 10. So 10 seems to be the best. And again, the reason you can see this thing of more predictors is worse, the root mean squared error is calculated on the test set. That was a very important step that maybe I should have made a bigger deal out of, which is that when we're calculating the root mean squared error, it's not the R squared value reported by the model. How did I calculate the root mean squared error? It was this line where I took the test set and I predicted what you would get on the test set, and I took I squared those up and added them. It really is the test root mean squared error. So maybe it would be even better for me to say a root mean squared error on the test set. So that's important. Okay, and that is why it can go down and then up. And look at this, I have a nice U-shaped curve here. So now I could talk about overfitting, how the model with all 18 predictors is overfitting compared to the model with 10. You can see this nice U-shaped curve, and you pick out the minimum. Okay, questions or comments about this one? So that's your 10 predictors. You can submit that model, run it on the leaderboard training set, and submit. Questions or comments? So I will say one thing. If you take the model with 10, right, the model with 10, that is this model over here. And so in this column, it's telling you these are the 10 variables to use. Here is the model. That is a scikit-learn object. You can run predict on it. If you just take that model and you run it on the leaderboard test set, the real test set, and you submit it, that is a good thing to do, but you are not being as performant as you could be. There's a step you're missing, and if you just take this model and run it, you could be doing better. Does anyone know what that step is? Yeah?
And that we should take the entire training set because we will only have a chunk of it.
That's very nice. That's exactly correct. So right now, this model was only trained on the training set that I picked, right? Because remember, I was cutting some of the data out so I could compute the root mean squared error. And so if you submit this model, that is a model that is trained on a subset of the training data you were given, right? So out of 1,000 houses, it was only trained on 800 houses or something. So before you submit to the leaderboard, to make a better model, we should run something on the full training set. And then, when we run something on the full training set, then it will be even better. So we won't be able to measure how good it's doing. We won't be able to measure the root mean squared error, but that's fine. We've already measured, we've already made our choices, and then we just run it on everything we submit. So, what should we do? How do we do that? How do we do that? What features would you use? We're going to run something on the full training set.
We will use the same.
Yeah, should we just use these 10?
Yeah.
That's the best 10, right? That's one option. You could run it with those 10. Can we do better than running it on those 10?
How about we shuffle our training set?
Oh yeah, okay, this is a great idea. You could rerun it, pick a new training set, run the whole thing again, and then, okay, now you have this one and that one. It's the alternate universe version of this. Which one is better? Which one do you pick?
This is our best guess, I think so. We should take this one.
I think this is our best guess. Something about this is our best guess. Is that something, this list of 10 features?
Yes. I mean, these features, list of features are the perfect predictors, I think.
They are the best predictors of size 10 on the training set we have. All right, okay. We would like, yeah, so you can rerun it and you can see, did it change? This would be great. If you ran it like 10 times and it's never changing, then that's good evidence in favor. So one way to get at it is to rerun it on a new training set. In the videos, they mentioned a different idea, a different way you could do it. Does anybody remember what that is? I'll let you think. What could you do? What else could you do other than rerunning it? That's a great idea, to rerun it on a new training set, or to do a leave one out, or a k-fold, or something. But there's a different way you can generate a list of 10 features. That might be even better.
Correlation between the
Yeah, correlation. What about correlation?
we find the correlation between the like different features and
Yeah.
compare and take the best in features and compare.
Yes, this is a very common idea. I'll talk about this one in a minute. This is a very common idea. So look at the correlation between the variables and try to use that to help you somehow. Okay.
So basically, if we are developing at a larger scale, then
Yeah.
I think we can go for a manipulation and visualization step. Like in it, we will look carefully at each features, missing values, clean them, and then we'll also process them and find out which features are more important. Then we'll go for it. I mean, like what Aman
Yeah.
is teaching us.
Yes. I mean, okay, so this is true. This data set happened to have the property. I just deleted all the ones that have missing data and stuff, so this one was like very clean. But there is one other thing you can do other than taking these features directly. I'll give you guys one more minute to think. Okay? Throw out some ideas. I think you guys are scared of having the wrong answer. I am scared that you don't have any answers. That's what my fear. We need to come up with lots of bad ideas, and one of the bad ideas will be a good idea. Okay, so what did we actually do? We did a train test split so we could calculate the root mean squared error, right? And then we used just the training set, and we did this whole shebang of run the regression on the training set, pick the best feature, then run the regression on the training set, pick the next best feature, and so on. Could we improve running our regression a little bit? How can we improve our running our regression? Say in this one, these regressions, we ran it with at-bat, and that is a particular model with a particular slope. And that, I claim we could come up with a better model. Option 0 was doing the at-bats. I think there's a way we can make a model that still uses only at-bats, but is a better model. A more accurate model that will more accurately capture the data than what was run here. So this one had an option 0 at-bat, and it computed the root mean squared error by measuring on the test set. And that 410 is an estimate of how it will do, of the model that we ran. But we could come up with an even better model that just uses at-bat. It would cost us something, but we can come up with an even better model. Still only using at-bat. So still doing a y equals mx plus b with only one variable, but just having a more accurate estimate for the slope, for the beta hat 1. Yeah?
Instead of running the model on the training set, you can run it on the entire data.
That is exactly right. So this one, option 0, was run only on the training set, and then the second line, the root mean squared error, was calculated on the test set. And that is why we trust the root mean squared error. But we sort of had to give up. This was the big thing that you have to give up when you do test sets, is that you give up the size of the training set. So our option 0 is not as good as it could be. We could come up with a better option 0 that's more accurate by running it on the entire set. We would give up. We can no longer calculate the root mean squared error. So if we do this, we'll have more accurate models, but we will not know when to stop, right? This nice graph that we had over here, this graph will no longer be a U-shaped curve, right? Because we won't have an accurate root mean squared error that tells you what to do. However, what we could do is we could say, look, we know that you're supposed to stop at number 10. We know that 10 predictors is the best. So if we could do it again, we would expect the same kind of U-shaped curve that would still have a minimum somewhere at 10, right? So we could just pick, instead of picking out from this curve, picking out this as the thing we take away from the curve, which is that we want the model that has C runs put out, C walks, so on. The thing we could take from all this discussion is we could say the magic number is the number 10. We just copy paste the number 10, and we say we're going to do the whole thing again on the full data set, and we're going to stop at 10 variables. So the thing that we've learned by this whole experiment is that 10 variables seems to be the best for this problem. Not that it's these 10 variables, but that it's the 10 variables you find. Okay? And by doing that, you're going to have a more accurate thing. Because these things, each of them, you should think of them as having some kind of, they are not the real thing, right? They're always in your training set, you're doing a measurement that is correlated with the truth of reality. And the bigger your data set, the more correlated with the truth. But we even made it less correlated by taking some data out to do our test set, which we had to do. We had to do that. That was like, there was no way around that. But now that we know the number is 10, let's do it again and use the bigger one. It'll be even more accurate. And that is what is done in the rest of the model. So use the entire training set, no test set, and it just redoes the same exact thing, same exact code, except for there is no test set. I'm using the entire data set as both my training set and my test set. So of course I shouldn't call it the test set anymore. Now I should just call it, this is the root mean squared error on the training set, right? So when it says root mean squared error, now it means root mean squared error training. This is something you should be very clear about in your project. When is a root mean squared error? When is it a test set error? When is it a training set error? Because they're like completely different beasts. So see if you can predict. We're going to make a graph that looks just like this graph. Predict in your head, what is the graph going to look like when I plot what is called the root mean squared error, the RMSE, versus the number of predictors. It's going to have a certain shape. Predict what it's going to look like. Okay, so we ran the same exact thing. And the point is, you're getting very similar things, except for the models are different, right? So the model number 0 at bat is now using the full set. It's more accurate than the model before. Okay, so very similar stuff. Run the same thing. It's still using the root mean squared error to make a choice. That root mean squared error is not the test set error, but it's the best thing we can do. Okay, and when you do all that, here is the graph. So here we ran it again, p squared runs again, and here is the graph. That is what the graph looks like. So hopefully you were able to predict this graph should always be going down because the root mean squared error means the training set error, and the training set error always goes down as you add more parameters. So here, it's always going down, but we know from our experiments before, stopping at 10 is the right thing. So the training error, even though we can't see it, the training error is always going down. The test set error, even though we can't see it, we think should be going down and then up with a U-shape stopping at 10. And now we can look at the model that has 10, and we can compare. So here is the final comparison. In our first run, these were the 10 variables it chose. And doing it with no test set on the entire thing, these are the 10 that it chose. And it chose, they're very similar, there's one that's different. There's this C at bat. It's saying, please use C at bat. I don't know what C at bat is. So, I don't know. They all start with C. What is C? I don't know. Anyway, so C at bat apparently is better than doing it the other way. And so this last model still has 10 variables, and the 10 variables are slightly different, and that presumably should be a little bit better. And this is one of the lessons in the video, is that this step of rerunning everything at the end, you use the training test set split to make your decisions, and then at the end you want to rerun as good of a model as you can using the entire set. And that'll be perfect for you guys because you have the nice leaderboard. You'll be able to submit to the leaderboard. You could even submit both and really see, is it actually better? So here's the leaderboard. Okay. Any questions or comments about that one? Okay. I have one more thing here. And this is a really common thing that I've seen people do. So for variable selection, they do this thing where they pre-select using correlations. So let me show you this little notebook that we did where we're pre-selecting using correlations. Okay, and this is one of these mathy ones that I invented, where there's some secret data that I invented according to some equations, so I know the equations. And I made a bunch of data. I made 5 x's, x1 to x5, and I made 2 different y's, y1, y2. Okay? And this is something people do. They say, okay, suppose we had x1 to x5, and we wanted to pick which one was the best. We would just, before we do anything, let's look at the correlations of the x's, and we'll do something with the correlations. We'll take the ones that are correlated, we'll like reduce the variables. This is something people do. So they'll plot, this is something you see online, they'll plot something like this, which is a correlation of the x's. So here are x1 to x5, and what is the correlation with the other x1 to x5? So of course on the diagonal is the correlation of x1 with x1, that's a perfect one. What's the correlation with x2 with x1 is 0.8, and so on. So you have these correlations, and so sometimes people will look at this and say, oh, the x1 is really highly correlated with the x2. So let's delete x2 because like x1 is already highly correlated. And they'll make up rules like if it's above 0.8, delete it or something. In this one, they're all correlated with each other. All of them are correlated. X1 is correlated with x2, x2 is correlated with x3, x3 is correlated with x1, not as much, but still correlated. So I don't know which ones you would delete in this case. You would have some rule, maybe you would delete x5 or x1 or something, but they're all correlated. And here is the whole point of this thing. These x's, we're only looking at the x's. I want to convince you that just looking at the x's, you will never know what is the right thing to do. And the way I'm going to convince you is we have y1 and y2, and the same x's for the y1 do one thing, and for the y2 do something completely different. So by just looking at the x's, you will never know what's going on, because it could be these same x's lead to two different things for the y's. So if you do this thing with the reducing correlations, is not a good step to do. Sometimes you're forced to, maybe you just have too much data to run it on your computer, but there's always like smarter ways you can do it. And so I'm going to show you on the y1 and y2, they have very different behavior. So to start with, if you do just y1 versus x1 and y2 versus x2, you get pretty similar results. So if you just do any one variable, they won't look that different. So here it is. They both look pretty similar. And I did a test set and a train set just using the ordinary thing. And the way you can see that they look really different is to do just a repeat of what we just did with the baseball data, is to do that forward variable selection. And when you run the forward variable selection, even though it's the same x's for both, they have an extremely different behavior for the y1 and y2. So I'm going to show you the two graphs you get by doing forward variable selection on the y1 and y2. So here it is for y1, and it's exactly the same kind of code as for the baseball ones, right? So it's trying all the models, it tries x1 to x5, then it tries, x1 was the best, so now do x1, x2, x1, x3, x1, x4, and so on. And when you do it, you get a model that looks like this. So this is for the y1. So for the y1, with only one variable, you have the best score, and then these other variables are just like making it worse, right? You're immediately overfitting. As soon as you have one predictor, you're doing great, and the other ones are completely overfitting. And you can say, oh yeah, the best thing to do is 1. And it's pretty noisy, right? So maybe you want to rerun it. But the best thing to do for y1 is 1 predictor. But for y2, if you run the same exact thing, here's what the graph looks like. And it's completely different. So same x's, exact same x's, but depending on the nature of the y2, in this one, you can see that it's going down for a while, and 4 is the best. So if you tried to do some like pre-selection, and you were like, I'm going to just delete things from the x's without looking at the y's, without looking at what I care about, you would make a mistake either in the y1 or in the y2. There's no way to look at only the x's and understand which ones matter. You have to somehow involve the y. And the best way to do that is using a train set and test set somehow. So if you have too many variables and you can't run this selection model, pick some other subset of models to look at, but you should still be involving the y somehow. So maybe you say, like, I don't have time to look at all p-squared things. So maybe I will group them into groups of, I'll make 5 groups, and I'll look at each of the 5 groups separately, but I'll still look at the y's, right? And then now instead of being p-squared, it's like p divided by 5 squared or something. But you should always be looking at the y. Don't try to do something where you just ignore the y. Then you'll make a mistake. Okay, so y1 only depended on 1. 1 was the best. y2, 4 was the best. And in fact, if you peek at the secret function, how is the secret function made? Because you can't do that in real life, but you can do that for my toy model. Here's the secret data. So y1 was just dependent on x1, right? y1 just depended on x1. It was a constant times x1. And y2 is secretly x2 plus x3 plus x4 plus x5. So the forward variable selection is able to figure out which one it is, whereas just looking at the x's, you will never be able to figure it out. There's the same x's for both. So great. I'm glad that was brought up. Any questions or comments about this method? This is a more of what not to do. Anything you do should be involving the y's and involving a training set or a test set. Okay, in the last few minutes of class, I have some practical things, and here are 3 practical issues that will come up when you do this data set. Some of them we've talked about a little bit, but feel free to chuck in any answer you want and we'll talk about them. So one question is, should you standardize the data? This means taking the data you have and before you do anything, sort of normalizing it, dividing by constants, subtracting means, stuff like that. Is that worth it? Should you? Number two, this is a big one that comes up in real life that I have talked about almost none in this class, is what do you do if some data is missing? So I think you talked about that a little bit in your other data science class, but we can also talk about that a bit here. What should you do? There's lots of possible answers. Number three, we talked about a little bit, how do you convert categorical data into a number for a regression? And there are different possible answers. Sometimes people make big mistakes in this last one, so I'll warn you about some of the big mistakes. But put in your favorite answers for any of these. You can put in like, I don't know, for the ones you don't want to talk about. And we'll, in the last 20 minutes, we'll just have a class discussion about these different aspects or anything else you want to talk about for the project. Okay, I'll give you 2 minutes to think about this now. Feel free to chat with your neighbors, and then we will reconvene. Okay, 10 seconds left. Put in, it's good if you put in any answer so you get credit for being here. So just put in I don't know for all three if you don't want to actually put an answer in. Okay, let's take a look. Let's look at what people said. Okay, should you standardize your data? 8 people said yes, 6 people said no. Some other people said yes, some people said only if it differs a lot, and some people said it depends. And I think the answer is it definitely depends. There are some pros and cons to this standardization thing. Does anyone want to volunteer some pros or cons? Let's do this. Standardize? So there's some pros and there's some cons. Pros. Cons. Yeah.
So if the data is pretty like all columns have numbers that are in the relatively very small ranges.
Yeah.
Like the difference between them, like one is 1 lakh and one is only dealing with decimals, like 0.0 to 1 only.
Yeah.
If that bigger difference is there, then definitely we have to normalize it, because the one which has a higher value, it will pull the model towards it and it will make a bias.
Okay.
But if the numbers are pretty small and they are very correlated, then we can just let it be. Like, because standardizing or normalizing leads to data loss, and it can actually take our model away from the reality.
Okay, yeah. Let's write some of these things down. So I think let's list it as a pro, which is if the column values are very different. Let's say they are on different scales. If the columns are on different scales. So let's say like 0 to 1 versus tens of thousands, right? So one column maybe is like, I guess like the percentage of something between 0 and 1, and the other column is like how many thousands of square feet or something in your house, right? And if those are very different, then this can lead to a problem. You said that the model will favor this one. Like the model will be like, oh, the 10,000 numbers matters a lot, and the other number doesn't matter a lot. So some models will do that if they're like not set up right.
Depends on
In the model we are looking at, we always are, I mean, in the linear models, it's always like this. It's y equals, so for the linear models, beta hat 0 plus beta hat 1 x1 plus beta hat 2 x2. So in the linear models, we are multiplying by these numbers, beta hat 1 and beta hat 2, and we are just adding it up. And the computer will automatically change the scale of beta hat 1 and beta hat 2 to kind of undo this stuff. So it won't make a real difference in this model. So for example, if beta hat 2 is in the tens of thousands, or if x2 is in the tens of thousands, then beta hat 2 will be in the 1 over tens of thousands, so that when you add them together, you get the right scale. So for the linear models, it will take care of this automatically. You won't get a mathematical error. But I will say, the error you will make is that the beta hat 1 and the beta hat 2 will be completely different scales. And when you look at it, you'll be like, oh, well, this number is only 0.00001, and that number is like 7. So like maybe the 7 matters more. But actually, it could be the other way, because they're multiplied by tens of thousands. So the error won't be a mathematical error, but it will be an interpretation error. When these things are different scales, the betas will also be different scales. And it's easier to see them if they're all the same scale. So I'll write if the columns are on different scales, the normalization fixes that. So that's very nice. And I will say, if you want to do the other thing that we talked about, is if you want to do a nearby neighbor model, which maybe some people want to do, I encourage you to do whatever you think is exciting. If you do a nearby neighbor model, then you've got to make sure your distance function takes into account the size. Because if you do x1 minus x1i squared plus x2 minus x2i squared, then it absolutely will go wrong. So if this difference is in the tens of thousands and this difference is like 0.1, then basically this one doesn't matter. And so your model will be effectively ignoring the small numbers. So if you want to do a nearby neighbor model, your distance function, which before it was just the distance, should somehow take into account how big things are. And if you normalize, it will fix that problem for you. You could alternatively put in some constant. You put in like C1 or C2 or something. Yeah, so normalizing can fix, in some models, actual mathematical errors, and in other models, it will fix some interpretation errors. And the con is, you said there is data loss. Tell me more about that. I didn't understand that.
Like to normalize or standardize, we are taking already the data which is recorded is generally, we can say, a digital data. So we already lost the reality due to converting it into a digital data. And then once we are also treating it with standardization or normalization, so we are like dividing it by mean or max, or like doing something on it, applying log functions to it.
Okay, so yeah, so let's say we start with the number 1,000, 10,000, and then you say we take the log. Let's take the log. We say we convert that to 4. You're saying we lost some data. We went from 10,000, and now we have 4, and the data is gone. It disappeared.
Not 100% is gone, but some percent. I mean, if you are coming back from 4, some percent is lost. So if it is a very critical sensor data, like in medical field, like even smallest of changes can have a large impact, or in space, like the smallest angle can make a large impact of thousands of light years.
Sure,
so in such a way, it will be a data loss. So
well, but in this case, so let's look at specifically the function log 10. If I can undo log 10 by doing 10 to the power, 10 to the power x. So you take log 10, you convert it to 4. I can convert 4 back to 10,000 by doing 10 to the power 4.
Because it is 10,000, but what if a number which is not fitting properly and it gives
let's do 1,124. That will get converted to 4.02 or whatever, ... You're saying if you round it off by too much.
Yeah.
I see. Okay. This is good. So yes, this is true. If you're deleting some stuff and you're rounding it off, and then you delete things, maybe it makes a difference on the other side. I will say though, if you're going to delete something over here, let's say we delete at the 3rd decimal place, those things, I think there's a good argument that they will not make a bigger difference in the thing than, like, it's a 1 out of 1,000 thing over here to delete in the 3rd decimal place. That would be like making an error of size 1 out of 1,000 over here. So it is true, if you're like doing a lot of manipulations where you're doing rounding and deleting things, you can lose some data, but presumably this is like very small otherwise the rounding or deleting is going horribly wrong, right? Like if you round 4 down to 0, then it's bad. But if you round 4.02 down to 4.02 down to 4.02, then it's probably okay. But yeah, okay, we'll leave that on there. That's a good idea. So data loss, let's put that under rounding. I think is the most common way that would happen. This is like a mathematical con. I think there's some cons of like usability. What would be some like just making it harder for you to think about? What would be the con of standardizing? Let's say specifically let's look at one of the things in your data set is lot area. Lot area, which is thousands of square feet or whatever. So some house will be like 240, maybe say 24,000 square feet. The lot that the house is on is 24,000 square feet. And then you standardize this, and then this turns into a number which is like negative 0.7 or something. And then later on you're looking and you're like doing your data and like the coefficient, you're like lot area is a negative number, but areas are positive, right? And what you did is this is actually representing negative 0.7 standard deviations. So it's saying 24,000 is on the smaller side of all the houses we have. So it's easy to sort of forget that and get confused by the fact that some things are negative. This is also some of your coefficients, which would, like, presumably bigger lot size is always helping. Well, I guess the coefficient would still, the sign of the coefficient would still go the way that. Anyway, sometimes this confuses you when you have negative 0.7. Another thing that will be confusing is when you go to take the test set, and I think this is the biggest place this comes up, is, so you did this lot area thing, you have a formula that works in terms of standard deviations. And you've done the whole model, you've picked out your best model, you're like, these are the features, I got the whole model, it's all set up. And then you go to the leaderboard to submit your model, and you download the test data set. And in the test data set, there's some house that has 55,000 lot area. And your model will run it assuming that it was like negative 0.7. And it'll be like, what the hell is 55,000? So you gotta, whatever you do to your training set, you're gonna have to do it again to your test set. And that can also lead to problems. Like, how do you convert? So when you run it on the training set, do you include the test set or not? What should you do? And so I think a big con is usability, being able to run it on like new data. For you guys, you have the training set and the test set. So if you want to do some kind of standardization, I really recommend you put both the training set and the test set at the very top of your worksheet, and whatever you're doing to the training set, do it with the test set the whole way along. So if you want to standardize, like great, do the test set at the same time. Even if you're not going to use the test set for anything, do the same, whatever you do to the training set, do it to the test set, so that when you get to doing this last step, you will know how to convert the 55,000. So that's okay, and that's just a usability thing. And interpretability, sometimes it can be hard to interpret. What does it mean if the lot area is negative 0.7 standard deviations? And things like that. Yeah, but otherwise, you have some nice properties. So it's up to you if you want to do it or not. And it's totally your call, whatever you think will be better. And it sometimes can matter. So if you're going to do something where it matters, be careful. Okay. I think that's everything I want to say about standardization. Anyone have any more questions or comments about that? Okay, let's look at what were the other two questions. Now I've even forgotten. What do you do if stuff is missing? So I think you guys talked about this a little bit in the other class, so we won't go into huge detail. So this idea of impute is like put in some values. You could do either the mean or the mode or the median. They all have advantages and disadvantages. I will say if you standardize, the mean will be 0. So it's like putting in a 0. So that's a nice thing. You can also remove them if you want. You can remove them. Another option, you could try to make models, like if there's one column that's missing a lot of data, you could try to make a model that doesn't use that column, right? Like we're choosing which things to use anyway. Why don't we just say, well, keep the data but exclude the column? That's up to you. And so, there's and there's some automatic ways to fill the things in NumPy. Whatever you use, just explain it well and like why you chose to do what to do. If you have a way to test, I'm testing different ways, that's even better, but it is up to you, and that is a big real-life step that we're not spending a huge amount of time on because it really changes from place to place, right? In some situations, you have a lot of data that's really good. In some situations, you have lots of bad data, and you have to know the details of how you got it. Okay. Okay, last, how do you convert categorical data into a number? This is a thing. So some people are telling you the actual functions, which is great. I just want to point out in the last 5 minutes here, one mistake that is I saw a lot of people make in previous years. And that is, if you have, let's pretend we have something that could be red or green or blue. Okay, there's 3 types of houses. There's the red houses, the green houses, and the blue houses. Okay, there are 2 ways to do this, and one of them is get dummies, and then there's another one like get numerical. I won't say what the commands are because I'm going to get it wrong. But there's 2 sort of ways you can convert red, green, and blue into numbers that you can use in your linear regression or in your nearest neighbors or whatever. And one way is like this. You say color, and you say red equals 1, green equals 2, and blue equals 3. So that's, you have a new column called color, and it either has 1, 2s, or 3s in it. Before it had red, green, or blue. Another option is you could have 3 columns. You can have red, question mark, blue, question mark, or green, question mark. And I wrote them out of order because I just forgot green. But then it would be something like you have 1, 0, 0, or 0, 1, 0, or 0, 0, 1. And a lot of people, they like this one better. They're like, look, I only added 1 new column. Like I took the data, now I just have 1 extra column. I went from having 80 columns to having 81 columns. Not bad. Whereas this one, I had to add 3 new columns. And some of these things in your data set will have like 10 options. So you're adding a whole bunch of extra columns. They're like, that's too many columns. I don't want to deal with that. And so people tend to like this one and not that one. But can someone tell me what is wrong? There's a serious problem with this one. There's a serious problem with this one. Yeah.
It's possible that while predicting the numbers go between 1 and 2.
Well, we only ever predict the y values. This is the x value. So, right, we're never going to have to predict the color of a house. We only ever have to predict the sale price of a house. And so we're just going to take as input what is the color of the house, and we can predict the sale price. So if this was a y value, I would totally agree with you. But this is only the x values. So we never have to predict these. So that's not the problem. Yeah, very good. Good thinking. Yeah?
Model tries to draw a slope bases 1, 2, and 3, which indicates either a positive or a negative.
Yeah, okay, this is fantastic. So if you take this one and you feed it into your linear regression model, you will have beta hat color times x color, right? So it'll take this 1, 2, or 3 value, it'll multiply it by the slope, and it'll add that on to whatever you're doing. And this is what it will do when you do a linear regression. And so by saying red equals 1, green equals 2, and blue equals 3, you have actually said, whenever you see a blue, that's 3 times as good as a red, right? You have told the model, without thinking about it, that this means blue is 3 times bigger than a red, and green is 2 times bigger than a red, and a blue is 3/2 times bigger than a green. And you probably didn't want to say that. You don't want to presuppose anything about the colors. Like you have joined the blue hierarchy team that thinks blue is the best color by doing this. I guess if it's negative, it's the other way around. Right? If the coefficient is negative, it's the other way around. So if you do this 1, 2, 3 thing, and you put it in a linear regression, this is like totally wrong. Like you're taking this number and multiplying it. And the computer will do it, right? The computer's like, whatever, like I don't know, like you told me the number was 1 here and 3 there, and I just did my best. So the computer won't spit out an error, but you'll get a model where this coefficient makes like no sense. Okay, so if you do this one, and you do linear regression, it'll be totally crazy. Same thing with if you do a nearest neighbor model, because you've said that blue is closer to green, then blue is closer and red is further away. So it'll say like, oh, these green houses, they'll tell you more about the blue houses than the red houses. When actually, like, they're all sort of equally distant apart. So if you do this one, this 1, 2, 3 thing is fine for some applications, but not for linear regression or for a nearest neighbor model or anything like that. On the other hand, this one is perfectly fine. This is totally fine, because what you're going to have is you're going to have beta hat red times is it red, x red, question mark, plus beta hat blue times x blue, question mark, plus beta hat green times x green, question mark. Okay, and what this will mean is it'll say, if it's a red house, we add on this number. So all the red houses get this score added up. Maybe red houses are better, so this number is big. All the blue houses get this number added up. All the green houses get this number added up. And we're not telling the computer any relationship between red, blue, and green. It will figure out the best possible coefficients. Maybe it will turn out that they're all equal, and it doesn't matter. That's fine. But we aren't giving it anything that's saying that red is better or blue is better. Okay, I will say, sometimes you'll make choices, like you'll know. I think one of the columns in your data set is quality or something. Quality, which is like poor, there's like poor or like good or like very good. There's one column that's like that. Okay? And if you want to do poor, good, very good, you could do something like this. Like this will be totally fine to do the red, blue, green. But maybe you want to think of doing something like this in that situation, because you really like very good should be better than good. So it is up to you, and there's like, this way was definitely not wrong, but maybe you want to do something smarter. Or maybe you want to combine colors, like you want to put red and blue together, you can say red or blue. And so it's up to you. There's like a lot of things you could do, but just be sure, this is the one big mistake that I want to warn you about, is this one, of setting 1, 2, 3, and then just putting it in the regression without thinking about it. Don't do that. Okay, that's the only thing. Okay, I'll stop there. So enjoy working on your project this weekend, and I'll see you guys on Tuesday. The first draft of the project is due next Friday. Okay.